Okay, then I have the pleasure to introduce our next speaker. It's Carl Doersch. He is currently at Google DeepMind. He has done a lot of work on self-supervised learning, multitask, context prediction, CPC, BYOL. We are very excited for the talk, and the stage is yours, Carl.
All right, thanks. So hopefully everyone can hear me. So this talk is going to be as much about transfer as it is about self-supervised learning. And the reason is that I think that these two topics are quite interrelated. Oops. So, and the reason is that the kinds of big data sets that we might be able to download from the internet and train self-supervised learning algorithms on are not necessarily that representative of the kinds of tasks that we'd like our agents to perform in the real world. So for example, in robotics, you could pretty easily train a network on something like ImageNet and then run it on your robot, but it seems like roboticists don't really do this. And it's not that there's nothing in common between these two visual worlds. They're all 3D environments with objects operating according to physics and so forth. But it seems like the representations that you learn from ImageNet just don't have enough information about the kinds of 3D poses and 3D shapes of objects that robots would need to do grasping. So I think that this is actually a pretty good opportunity for self-supervised learning to kind of try and identify what features and what information actually does transfer so that we can help out in these kinds of domains. Now that might seem like a strange motivation to talk about transfer like this, since after all, the story that I think I've heard many times about self-supervised learning is that there's billions of images on the web. If we can use them all, then eventually we'll see enough examples of everything that we care about that the transfer is maybe less important. But the reality is that this hasn't worked out all that well. The state-of-the-art algorithms right now seem to train mostly on ImageNet, and efforts to use much larger data sets, the Instagram 1 billion and so forth, haven't shown that much of an improvement. However, it turns out that learning on ImageNet is good enough. As Aaron was mentioning, if you train on a network with self-supervised learning on the same data, you actually do better than one that's trained in kind of the naive supervised way. So this indicates that there might be a slightly different story that we might tell ourselves, that self-supervised losses don't just let us use unlabeled data, they can also help us generalize better. So why might that be the case? Well, I would argue that generalization is really about inductive biases, and it might be the case that we can actually learn inductive biases that will help us on downstream tasks. For example, one inductive bias you might use is that novel scenes tend to be composed of familiar things. So even if you haven't seen a centaur before, if you can realize that this object is made up of people and horse parts, then that helps you learn about this category much more quickly than if you tried to train things from scratch. So if we can use self-supervision to learn representations that decompose into simpler pieces, such that the representations of novel scenes or objects or tasks make it clear what's similar to familiar ones, then it's more likely that we'll be able to learn quickly. So there's many examples of possible inductive biases that we might try to train. And in all cases, I think that really knowing whether we've accomplished that goal is by evaluating on transfer to novel tasks or data set with few labels and also potentially with little data. So there's going to be two papers that I talk about that go in these directions. First of all, BYOL, which is about better representation learning, and then Crosstransformers is going to be about improving the transfer. So let's dive right in. Bootstrap your own latent is, I think, in some ways a response to kind of a common view of how contrastive learning methods are working. So I think the common story of why something like Sinclair works is that it's about instance discrimination. You're trying to tell the difference between each image and every other image in your data set. And at the same time, we're trying to learn some kind of invariance to the augmentations that are being applied to these images. And this story has always seemed a little strange to me because it assumes that random images are actually good negatives. And that means that you're going to be trying to tell the difference between two different images of golden retrievers and saying that they should be as different as a golden retriever is to a bridge. And that seems a little questionable. And so we're trying to see if there's another way that we can go about doing this. So BIAL starts with Sinclair, and for those not familiar, Sinclair operates as follows. You take a bunch of images, and for each image, you generate two views by applying some form of data augmentation, cropping, colorization, etc. And then you feed both of these into a neural network, and the loss function is going to encourage the representations of the two views of the same image to be more similar than they are to any other representation of images in the data set, according to the loss function I'm showing on the right. Now, it's straightforward to just get rid of the denominator and switch this over to the following loss function. But there's an obvious problem with this. If the network gives the same exact representation to every image in the data set, then this loss is going to be minimized. And that's not a very useful representation. So BIAL makes a couple of changes to prevent this from happening. The first is that it adds a stop gradient on one of these pathways. So the gradients are only flowing through what we call the online network, and the target network is computed as an exponential moving average of that online network. So unfortunately, this still doesn't train. We still get collapse when we train this type of network. But the critical element to actually make this train is to add the predictor on top of the online network, just another few layers of MLP. And once we have this, the results are beautiful. Now, there's quite a few results in our paper, and I'm only going to scratch the surface of them, but the summary is that at publication time, we had state-of-the-art on linear evaluation, on semi-supervised learning with few labels on ImageNet, and also strong results on transfer to Pascal detection and segmentation, NYU depth estimation, and also training BIAL on the places data set and then transferring to ImageNet. And in all cases, we are, well, essentially all cases, we are outperforming Sinclair by a comfortable margin. So BIAL works, but the question is why? And I think there's two sides of this question. First of all, why doesn't it collapse? Which I think we actually do understand this pretty well. And then there's the other side of like, what exactly is it learning? So first on the question of why doesn't it collapse? A lot of people have identified the target network as one of the new things that's different from Sinclair. And it's certainly true that if you don't have a stop gradient, BIAL's representation is going to collapse. That stop gradient is quite important. However, if you skip the moving average, it's still possible to make it work. The trick to make it work is to increase the learning rate of the predictor relative to the embedding network by a factor of about 5. So that's interesting. The predictor, on the other hand, seems to be critical. We haven't been able to train this without any kind of predictor, and I'm showing on the right-hand side a plot of with predictor versus without predictor. The without predictor you might recognize as being the mean teacher algorithm. And this is the variance of the representation, like a single unit in the representation across different images. So without the predictor, we're having the same representation for every image. So it seems like the predictor is really the critical part of this. So in order to understand why that is, let's first assume that the predictor is perfect. It's just a magical predictor that always does the right thing. And it's minimizing that the error in its predictions, and then assume that the target network is fixed. And from the standpoint of the optimization, the target network really is fixed because it has this stop gradient on it. It's straightforward to show that BIAL is minimizing the conditional variance of the target representation given the online representation. That is the fraction of the variance of the target that is not explained by any information in the online network. So it's straightforward to show that increasing the information in the online embedding can never increase the conditional variance, again, under the assumption that the predictor is perfect. Because in that case, if there's useless information in the online network, then the predictor is just going to ignore it. But if there is useful information, then the predictor is going to use that to improve its predictions. So therefore, the gradients we would expect would never reduce the information in the embedding, and it instead would try to increase it to predict better. Now note that this argument breaks down if the predictor is imperfect, that adding more information into the online representation might actually just increase the error, just because the predictor is going to misinterpret that and just add noise to its predictions. So I think that's a pretty good understanding of why this doesn't collapse. But what then does it learn? I would argue that BIAL is actually less about instance discrimination and more about context prediction. And I should point out that this is a bit more conjecture. We don't necessarily have proof for everything I'm going to say here, but we do have some evidence. One thing that we can look at is the importance of different data augmentations. And you can see that cropping is more important for BIAL, whereas color jittering is more important for Sinclair. If you remove those color augmentations, BIAL is performing much better than Sinclair. So why might that be? Well, one thing to keep in mind is that BIAL doesn't actually need to differentiate between all images. If you have two golden retrievers, BIAL can have the same representation for them as long as that representation is able to predict the stuff in the context. Whereas with Sinclair, in order to differentiate between those two, it may be latching on to some kind of low-level pattern that's different between the two golden retrievers and using that, which is maybe not what you want. So in that sense, BIAL is an easier problem than Sinclair, but BIAL is harder in a different way, in the sense that BIAL's loss doesn't saturate when the positive pairs are similar. So imagine you have two patches that are highly overlapping. Sinclair can just represent all the information that's overlapping in those two patches, and therefore get representations that have a very high dot product, and then this loss is going to saturate, and there's not, it's going to be much more similar to each other than they are to other patches in the data set. And so Sinclair doesn't have much of an incentive to learn about the stuff that's not overlapping in those two patches. Whereas for BIAL, we have to do a regression. We have to predict all of the information that's in the other representation. And so it seems more likely that BIAL would have to learn to predict that stuff. And so context prediction, I think I've argued in the past, is a pretty useful method for self-supervised learning for a couple of reasons. First is that it requires you to recognize the parts of objects independently of one another. That's the whole recognition problem. You have to recognize one part to be able to predict the other part. But it also means that we can just recognize the parts independently, which means, as I was mentioning before, we can recombine them in ways that help us generalize. And so on that note, I'm going to talk about Crosstransformers, which try to do this more explicitly. So thus far, transfer has actually been a pretty important but maybe unsung hero of the self-supervised pipeline. So far, we've just kind of used fine-tuning off the shelf as kind of the right way to do transfer. But there's a whole literature in the few-shot recognition domain which aims to train on one data set, and then at test time, it's going to have to learn rapidly some new categories, maybe in a new domain, and learn to classify between them. And I would argue that in order to solve problems like this, the challenge is to represent new objects in terms of familiar ones. So let's take a closer look at how this task works. We generally have a support set, which consists of many, or a small number of images from a number of different categories, and then query images that we have to label. And this is all, again, at test time. So you might assume that a neural network that hasn't been trained on these particular bird categories, but has seen birds in the past, maybe it should know enough about beaks and feathers and so forth that it can say what these images have in common. And indeed, this is a pretty good representation. State-of-the-art algorithms like prototypical networks make use of this in the following way. So you first represent all of these images using a neural network, and then do global pooling at the end to get a single feature per image. And then for each category within the support set, you first you compute a prototype by averaging the features across that category. And then you compare each prototype for these classes to the query using some distance function. And at test time, this is the end. You take the class with the minimum distance as your output. But you can train this algorithm on episodes as well or on support sets and query sets from the training set as well to produce, and you do this by treating the distances as negative logits and plugging them into a softmax classifier. So this works, but what is it really assuming happens for these held out categories? I argue that prototypical networks must capture similarity for these held out categories. That is, they must represent new categories in terms of familiar ones in a consistent way. But does it actually work this way? Let's find out. So we split ImageNet into training and testing categories, and then we trained representations with prototypical networks on just the training categories. And then we can look at the representation learned in prototypical networks and find nearest neighbors for test category images in both the training and test sets. And if things are working, we hope that we'd find the correct test set category out of this whole data set. But it turns out that this doesn't really work. And not only are the retrievals pretty close to random for test images, we see some pretty strange patterns. So for example, this screw has retrieved a bunch of buckeyes as its nearest neighbors. And so I suspect what happened here, and I should point out that there are plenty of screws in this retrieval data set that it did not find. So I suspect that what happened here is that the network sees this brown round object on a gray background and says, hey, I've seen that many times for the buckeye category, so this is probably a buckeye. And then for the prototypical network loss, it helps to have the same representation for every single buckeye in the data set because that's what the loss is penalizing. So the network then tries to throw away all the extraneous information and just summarize this image as a buckeye. And it's not just this image. There's other examples like this bassoon matched with letter openers. This knot is matched with a bunch of Gila monsters. And so this is kind of a persistent problem. Of course, there's many other examples where this doesn't happen that I'm not showing, but this does seem to happen occasionally. And so in order to solve this problem, what if we could force the algorithm to compare the texture on that screw directly to the texture on that buckeye? Then maybe it might realize that there's some feature, this groove, that's not appearing elsewhere, and therefore it should be a little bit less confident in its predictions. So this is the intuition behind cross-transformers. And to make it a bit more explicit, imagine you're trying to classify this bird. You might be able to tell that this is a towhee and not a tern. But in order to justify this, you might say something like, well, it's got this tuft of red feathers on its head. So in order to do that, what you implicitly did was first decompose the object into simpler, more local parts that could be put into correspondence, namely the head of this bird. And then once you found that the correspondence, you compared the local features. And maybe you haven't seen this particular breed of bird, but you have seen red tufts of feathers, and so you can do this comparison correctly. So cross-transformers are going to try to do this. That is, bring features from the support set into correspondence with the features in the query image. So we do this by modifying prototypical networks by first replacing that globally pooled feature with a full set of convolutional features. And then for each spatial position within the query, we try to aggregate relevant features from the support set using a transformer-based architecture. And so this results in a set of aligned features that's the same size as our query features. And then we can compare these position by position to get a set of distances that we then average to get a single distance, which we use exactly in the same way as in prototypical networks. So transformers, just to summarize how that works, you get the support set features and the query features, and you compute a set of keys and queries for both of them. And then you compute dot product attention for these keys and queries to get a set of softmax normalized weights for each spatial position P. You then compute a set of values from your support set images and do a weighted sum with these attention weights to sort of aggregate all of the features that might correspond with position P. And that gets you the position P within your query aligned prototype. And you can repeat this across space and then match this query aligned prototype with analogous value features from your query image. So this is a good story, but what happens if the features have already collapsed to categories before we even apply this transformer? Say the representations of all of these buckeyes are exactly the same. That's not going to be very useful if at test time we need to differentiate between categories that have shells and categories that don't have shells. So we'd like to try to keep some of the information that makes these images unique. And we're going to do that with the standard self-supervised trick of instance recognition. Specifically, we're going to adapt Sinclair to this domain. And it turns out that we can do this without even changing the network and without adding any extra heads. Note that prototypical networks and cross-transformers train on episodes, that is the support set and query set. And so we can actually convert episodes and train for instance recognition just by adding some episodes that require this kind of instance recognition, which we call Sinclair episodes. And really producing them is quite straightforward. Starting with an episode from the training set, we first throw away the labels and replace them with a different label for every image. And then we throw away the queries and replace them with images sampled from the support set. And then we apply some data augmentation as you would in Sinclair, and the result is an episode that requires whatever episodic learner we're using to do instance recognition. So now to evaluate this, we use the metadata set benchmark, which is actually a pretty cool benchmark. The training is going to be a subset of ImageNet categories, and then testing is going to be transfer to a bunch of different data sets, each independently. And each data set illustrates kind of a different kind of transfer. So for example, Omniglot is completely different object categories in a very different domain. Aircraft is kind of the other extreme, where there are aircraft in the ImageNet training categories, but they are all in a single category. And so if they all get the same representation, then you're going to struggle to differentiate between 100 different categories of aircraft at test time. So first, let's look at some qualitative results. I'll show a query image and then some correspondences in the support set by first picking 3 points within the query, red, green, and blue, and then showing in corresponding colors what are the attention maps found by the cross-transformer. And here you can see that wheels are matched with wheels, noses are matched with noses, etc. This attention doesn't need to be one-to-one, so with these flowers, we're finding multiple instances of flowers to correspond to, and it also doesn't need to be fine-grained. So with this bird, we have different fine-grained categories of birds, but then the algorithm is still finding good correspondences, which suggests that the correspondence is kind of coarse-grained, followed by a fine-grained comparison of the local features. Now let's talk about some quantitative results. Cross-transformers outperform prototypical networks by a pretty substantial and pretty consistent margin. And note that we're kind of used to seeing like MS-COCO or ImageNet results being 2% better and that being consistent. And here we're seeing, on the order of 10% better. This is not necessarily true of other baselines. So fine-tuning, the famous, default that everyone uses in self-supervised learning, performs very well on some data sets relative to prototypical networks, but worse on others. And furthermore, adding Sinclair episodes on top of all this improves as well. We can also compare this to more recent state-of-the-art algorithms from this year, and you can see that we are still performing better. These tend to use like more complicated data augmentation that I'm not going to go into, but we're applying that as well, and we also get benefits. All right, so let's take a look at the bigger picture a little bit. So what have we really accomplished with cross-transformers? I think we've shown that they can learn and exploit correspondence without explicit supervision for it, and this is really useful for transfer. We did use labels in order to get this kind of performance, but I think that we don't need to. And there's been a lot of recent work in, say, optical flow on constructing losses that can find correspondence without supervision. So I think that's a cool direction. And then, of course, we use Sinclair Episodes, which are a self-supervised loss that guides the features in order to prevent the collapse and improve the whole algorithm's ability to generalize. And so what is next? That's the title of the workshop. Well, I think that transfer is a particularly understudied problem, and one that we should be paying more attention to. We need representations which distinguish the properties that transfer from the ones that don't, and I think self-supervised losses may be a good way to accomplish this. And maybe a little more broadly, I think that vision has a tendency to pick an existing solution and hack on it. And this is a good thing, but it does have this risk of kind of running into local minima, and everybody's working on the same thing, and nobody realizes that a wildly different approach may improve things. And there's a couple of examples of this in this work. Everybody's using linear evaluation and fine-tuning, but maybe this is not the right thing that we should be pushing towards. And also contrastive methods. There's been a lot of work engineering contrastive methods, but maybe they weren't working for the reason that we thought. And we have a simple way of extending Sinclair to not rely on this, but maybe if the difference had needed to be larger, it would have taken us longer to find that. There's many physical truths that self-supervised learning could exploit, but it isn't. Things like the 3D properties of the world, or the physics, momentum and so forth. And I think that maybe the algorithms that exploit these will be weaker to begin with, but eventually will contribute. And so I think that the solution for this is downstream task diversity. That when we write papers, maybe we should not just run on the one benchmark that everybody else is using, but instead try to find new benchmarks that maybe we don't have any comparisons to, but later works can then try to beat us on. And I think that that's going to help encourage these other algorithms that can exploit different properties and hopefully get us to the solution to all of these problems faster. And I'll stop there. Thank you.
Thanks, Carl. That was a very interesting talk. We do have time for a couple of questions, and maybe while they roll in the chat, I have a question that is related to the emails we have been sending before the workshop, actually. And I thought it would be interesting to discuss. It's about your thoughts on the topic that in the beginning of self-supervised learning, we've seen all these very interesting and very interpretable tasks like colorization, rotation, jigsaws. And now everything has moved to less interpretable tasks like contrastive training. What do you think? Why did this happen? And why is it necessary to train with these kind of not really intuitive tasks?
Right. So I think the problem is that, of course, the tasks that we can interpret, these relative position or colorization things, are not really training for properties that we actually care about, at least not directly. It's kind of an accident that these things correlate with the kinds of representations that we do care about. And so I think that we want to improve. Sorry. Yeah. So I think it's kind of an accident that these algorithms improve on these tasks, and so I think there's no necessarily reason why we should expect that the correct tasks are going to be interpretable in any way. And so I think that in many ways, we just started with interpretable tasks that just kind of correlate, and then we've been doing a bit of hill climbing to improve on these based on what's the empirical results. And I think that's good. I think that that's going to be necessary in order to get the kind of best results that we can get. But it also makes it less clear what these algorithms are using. And I think that, as I mentioned, the kind of diversity in methods is going to be important long term. So I do worry a little bit that maybe we would lose, if we don't understand what these algorithms are exploiting, that's going to make it difficult for us to find things that they aren't yet exploiting. So to some extent, I do feel like we need research in both directions, both in terms of just trying to get the numbers as high as we can, but also in trying to interpret what the algorithms are actually doing.
Very interesting, thanks.
So in that vein, I think we have time for one last question, since we also started slightly later. Bram Wallace asks, have you studied the representation space of BYOL versus MoCo versus Sinclair? Are the features distributed similarly despite the training differences?
So I'm not aware of explicit ways of visualizing the features that really are that informative. All that we can really say is, in terms of the performance on downstream tasks. And here, I think, we don't have a lot of instances where BIOL seems to be performing astoundingly different from Sinclair. And I think that that's maybe a little disappointing that we did spend some time trying to find tasks where things work better, and we didn't see any. But that said, I had the slide on kind of explaining what are the differences, at least from a philosophical level, of what what the differences are between what BIOL and Sinclair are learning. And I hope that people can take that and run with it and try to hopefully find tasks where things do perform differently. I do admit that a lot of the tasks that we are evaluating on here are just image tasks, and not necessarily that different distribution. There are some similarities between Pascal and ImageNet. So I think that this is a really interesting direction for future research.
Cool. Yeah. Plenty of exciting stuff still ahead.
Okay. Unfortunately, I think we have to move on to our next speaker. Thanks a lot for giving the talk and joining the question session.
Thank you.